Hello. Today we are going to talk about state reduction and minimization of the circuits. We know that when we analyze a sequential circuit, we start from a circuit diagram and it culminates to a state table or state diagram. So we start for analyzing or analysis of a system. We start from circuit design and culminates in a state table or state diagram. Okay, so on the other hand, when we design a circuit, we start from a set of specifications. So we start from a set of specifications, and the result is a logic diagram. Okay, so let's say we are analyzing a system and we have a state table. The state table has some states. So it starts from A up to N. So we need flip-flops to implement the states. If we have four states, we can implement these four states using four flip-flops. Why? Because 4 is equal to 2, we can implement it with 2 flip-flops because 4 is 2 to the power of 2. If we have 5 states, we should look for the smallest number in the form of 2 to the power of n, which is bigger than 5. So the smallest number in the form of 2 to the power of n, which is smaller than 5, is equal to 2 to the power of 3, which is 8. So if our state table has 5 states, we need 3 flip-flops to implement the state. Okay, so more states means more flip-flops. More flip-flops means more complexity and more circuits and components, and so the system will become more expensive and slower. But sometimes when we look inside in a state table or a state diagram, we see that some of the states are redundant. Some of them, in fact, are repeated. So we here in this lecture, we are going to find like redundant states and remove those states from our state tables so we can reduce the number of states, so and as a result hopefully reduce the number of flip-flops. So we need to find redundant states. So let's see what states are equivalent. So we have a definition. We can say that two states of sequential machine are equivalent if for each input they produce the same output, and their next state or next states are either identical or equivalent. So if we have two states, state A and B, if they produce same output for the inputs, same outputs, let's say if input is 1, for example, for both of them, if they produce same output and their next state is also same, identical, so if the outputs for same input is same and the next states also are same, we can say that states A and B are equivalent. Okay, so what we can do when we find two equivalent states, when two states are equivalent, one of them can be removed without altering the input-output relationship. So when we found two states which are equivalent, we can easily remove one of them, and nothing's gonna change in our circuit. Okay, but how we can find or determine equivalent states? So how to determine equivalent states? We have several methods to find or determine equivalent states. Here we are going to talk about two methods, method 1 and method 2. Method 1 is inspection, and method 2 is partitioning method. What is inspection? In inspection method, look for the multiple identical rows in the state table. So we look for multiple identical rows in the state table. Okay, so for example, here we have one state table which has 4 states. X is 0, 1, state A, B, C, D. And let's assume we have this state table. Okay, now if we look to different rows, here we see that row B and row C are exactly equivalent. So B and D, sorry. So we can say that B and D are equivalent. So we can remove one of them. Okay, we can remove one of them. No matter which one you remove, you can remove one of them, and of course you need to substitute the data state with the other state which you keep. So here, if we remove state D, anywhere in our table which we see D, we will replace it with B. And of course, we get rid of this state, okay? So we keep X, A, B, C, and now we fill this table. So we say B0, C1, C0, A1. For C here, if you look, we see that we have D here, D. But state D is removed, and as I said, we replace all these with B. So we say B1, B0. And this one is the equivalent or reduced state table. So in like before minimization, we had 4 states, but after reduction we have only 3 states. Okay, so the second method which we are going to learn is partitioning. Okay, so partitioning has some definitions. First, I prefer to write on the definitions for you, and then we are going to do some examples and see how this partitioning works. So let's go with some definitions for partitioning methods. Okay, so first of all, what is a partition? We can say a partition consists of one or more blocks. What is block? We will discuss. Where each block comprises a subset of states that, here is important, that may be equivalent. May be equivalent. So it's the blocks in the states in a block may be equivalent, but the states in a given block are definitely not equivalent to the states in other blocks. So what does this paragraph says? It says that we have in partition, we have different blocks. Each block has some states. The states in a block may be equivalent, but 2 states in 2 different blocks are definitely are not equivalent. Okay, so what's the method for doing this reduction? We have some definitions again. The first definition is successive partitions. What is each partition? What does each partition means? So successive partitions P sub k. P sub k. Each P sub k is composed of a number of blocks, each block having one or more states that are k equivalent. Okay, so this is the definition of partitions. So let's see what steps we take to solve a partitioning reduction. So step 1, partition P1 is formed by placing states in the same block of P1 if and only if outputs are identical for each possible input. Okay, so this is partition P1. Step 2, successive partitions are derived by placing two or more states in the same block of pk if and only if for each input or input value the next state all lie in a single block of p sub k minus 1. So after we put the different states in the same block which have identical outputs for each possible inputs in P1 for the successive partitions, we put the states that have the same next state, in fact, in same block. So step 3, when P sub k is equal to P sub k minus 1, then the state in or states in each block are equivalent. Okay, so it is some methods, definitions, how partitioning works. It might be seems a little confusing based on these definitions, but in the next lecture we are going to solve some example and we see that how easy we can find the identical or and the redundant states.